A final test of general relativity comes from another prediction that has perhaps the most exciting implications of anything that comes out of general relativity. And that's the prediction that if space-time is warped by mass, then just like a rock thrown in a pond, the movement of masses should create tiny ripples in space-time itself, what we call gravitational waves. Now, these ripples in space-time are going to be extremely small and therefore very, very difficult to detect, and any that we hope to detect would have to come from large objects. And so for 100 years after the development of general relativity, nobody expected to be able to find gravitational waves until the last few years. And finally, 100 years after the publication of general relativity, gravitational waves were discovered.
Tremendously exciting news. Gravitational waves have finally been detected. Here's a brief explanation. Back in 1915, Albert Einstein gave the world his new theory of gravity, the general theory of relativity, which is based on the beautiful idea that gravity is nothing but warps and curves in the fabric of space-time. Now, barely a year later, Einstein pushed this idea one vital step further. You see, he realized that if space is flexible enough to warp, then it should also be able to ripple, to vibrate, to undulate. And that would mean that if something were to jostle the fabric of space-time, it should send out ripples in the fabric of space, and it's those ripples that we now call gravitational waves. Now, of course, the source of gravitational waves would not be my hand jostling space. Instead, it would be some highly energetic astrophysical process like rapidly orbiting neutron stars or black holes that would send out a steady rumble of gravitational waves. Or at least, this is what the theory says should happen. Now, how do you test this idea? Well, the math shows that as a gravitational wave rolls by, it will squeeze and stretch anything in its path. You see it happening here for the Earth, but of course, it's not exaggerated so you can see the effect. When you do the calculation, you find that the amount of squeezing and stretching would be tiny, a mere fraction of an atomic diameter, and that makes it pretty difficult to detect. But that is what the LIGO team has now achieved. And they did it with two detectors, one in Louisiana, the other in Washington State. And in these detectors, what they do is they fire laser beams along two 4-kilometer-long evacuated tunnels. And when the light recombines, it creates an iconic pattern. It's known as an interference pattern. But the only thing that you need to grasp is that were a gravitational wave to roll by, it would squeeze and stretch the arms of the detector, and that would have a measurable impact on that interference pattern, causing it to shift. And it's just that kind of shift in the interference pattern that the LIGO team has now observed, the first direct detection of gravitational waves. And this is big. This will go down in the history of science as a pivotal moment. And not just because it's another spectacular confirmation of Einstein's ideas, which it is, but rather because for millennia, we have explored the universe using waves of light. This discovery marks the opening of a new era in which we will explore the universe using waves of gravity.
So this is tremendously exciting because it opens up a whole new window on the universe, a whole new way of seeing the universe. Since the dawn of time, ever since the first humans looked up into the sky, everything we've learned about the universe has been through the medium of light. Now, we've gotten much, much better at collecting light or electromagnetic radiation. First, the telescope that allowed us to collect much more visible light. Then, with the discovery of the other forms of electromagnetic radiation, we developed X-ray telescopes and infrared telescopes and all that. But all of this was collecting the same sort of thing, electromagnetic radiation. That was the only thing that reached us from space. Now we have a way of detecting a completely different phenomenon that comes from space that allows us to study what's out there. And we've already started to use it. This is from August of 2017, the first cosmic event observed in gravitational waves and in light, so that we could compare them and learn some things from the gravitational waves and compare them to what we learned from light. In January of 2020, a burst of gravitational waves hits our planet. Astronomers have no clue where it's from. So researchers don't know where this burst came from. There's some phenomenon out there that may be something we've never, ever encountered or imagined before. And just recently, in April of 2020, a collision of black holes of different masses were detected using gravitational waves. So this is tremendously exciting, an entire new way to study the universe, and who knows what it will reveal to us. So just to give you a sense of that, there is an article, I've posted the link on the Google Classroom, and you can read this article, The Gravitational Wave Revolution is Underway.